Thank you. Hello, everyone. So my today's talk is going to be about the applications of solving the policy diffusion problem in political science and how we do it with Apache Spark. This work is done in collaboration with Professor Koski and also Jim Pivarsky, both from Princeton University, and Jim's name will appear later in the slides as well. I'll start my talk with introducing the policy diffusion problem in politics and what makes it a data-intensive problem and how we approach solving it with Apache Spark. Then I will spend the core of my talk speaking about the modules or the stages of the pipeline and how we put this all together. And mostly I will focus on the all-pair similarity, which is the most challenging part. In the last one-third of the talk, I will discuss about the interactive analysis with the histogrammer tool, which we introduce, as well as the GraphFrames for the graph processing part. So the policy diffusion detection is a problem from a wider class of the fundamental text mining problems of finding similar items. It occurs when the governmental decisions in some jurisdictions are systematically influenced by a prior policies in some earlier year in a different state. And an example of it could be the stand your ground bills, which is a type of laws about the trespassing and real estate. Originally, they were introduced in the South Carolina, Florida, and Michigan in 2005, and then after an incident involving Trayvon Martin's death, a similar type of loss has been introduced in pretty much every state, as you can see on the map here on the right. And we focus on the type of policy diffusion which can be detected by examining the bill text and calculating its similarity. Before we go into details of the pipeline, let me speak more about the hardware and the cluster setup that we use. At Princeton University, we deploy a Spark in two different ways. First, it's on our HPC clusters using the standalone deploy mode, allocating the resources with a Slurm resource manager. And another way is classic Hadoop architecture and scheduling applications with Yarn resource manager. For this particular task, I used the SGI Linux cluster with Cloudera distributions of Hadoop installed and high memory node instances. So as you can see on the Spark is a master worker, uses master worker architecture. As you see on the left here, it involves the centralized cluster manager, the driver program, which is usually run on the head node and which starts up the Spark context, which defines the directed acyclic graph and the stages of the computation. And then workers are launched on the executors, each having their own JVM inside the container, and one can run multiple tasks inside the JVM. So this is the picture for Scala or Java. For Python, it's slightly different. It uses Py4j sockets and resulting in slightly larger communication overhead. So that's why we actually implement this all in Scala, unlike many researchers in the field who use Python and R. So here's a brief overview of the text processing pipeline. And as you can see, there is three logical parts to it. First, from left to right, is the data ingestion. Secondly, the distributed machine learning with SparkML, and finally, the interactive analysis with histogrammer and graph analytics with GraphFrames. So for the data ingestion, currently we use only the static source located on HDFS. We consider in future using the streaming application with Kafka and Spark streaming. The data set used for the tests is based on the LexisNexis StateNet datasets. We contain 7 million legislative proposals for 50 US states, split by year and state. So the initial data set is an unstructured text document. As an example, you see here. So the first step, we structure the data and put it in the JSON format, and then we convert it to the binary JSON format with schema, the Avro format, which is very useful, has good interoperability with Hadoop and Spark, and it reduces the serialization time, which is a plus as well. So next, for the distributed processing, these machine learning parts. So here we have two main analysis workflows. The first one, it basically follows closely the latent semantic indexing. So we start with the general natural language processing workflow, where we clean and normalize our data, extract tokens, and bag-of-word features. Then we apply TF-IDF and truncated SVD. Speaking of the API here, these parts are data frame based, and unfortunately currently we have all the linear algebra in Spark is essentially a set of wrappers to BLAS, Fortran libraries, so it's Spark MLlib and RDD based API. So we have to do some conversion here of data frame and to RDD and back. Then we apply Kmeans clustering. So the goal here is not to only identify topics, but the groups of documents to focus on for the all pairs similarity comparison, which follows. The second workflow relies on the min hash and locality sensitive hashing. Parts of the feature extraction steps here are the same. And then here we have to use larger granularity for the n-gram, because we are essentially looking at the sets representing documents, and the frequency here doesn't matter. So if you use small granularity, it essentially results in all of the documents having the same sets of n-grams. And then we extract the characteristic, min hash characteristic matrix and signature matrix. After that, locality sensitive hashing is used, and the all-pair similarity is calculated with locality sensitive hashing. So before I continue, let's talk a little bit more about what is SparkML. There was a nice talk yesterday by Debit Sai with the introduction. So there is two remarkable things about SparkML. First of all is the standardized API, which it mimics that of the Python scikit-learn library. And the second thing is ability to take advantage of the data frames, the catalyst optimizer, and the direct operations on the serialized data. So the two main components of SparkML pipelines are the transformer, which essentially we can think of a user-defined function which acts on a column of a data frame and outputs the result of the transformation to a different column, and the estimator, which is usually like any model which we feed to data like Kmeans or an IDF. So here is an example. Basically, what we use for our analysis, we reuse a lot of the transformers and estimator from SparkML, which do like a standard NLP transformations like regex tokenizer, stop word remover, and n-gram extractor. But in addition, we also add our own. It is actually quite easier to add your own transformers. Here's a somewhat simplified example, which all it does is just cleans text. So all one needs to do is to extend the unary transformer class and define the logic of your transformation here in the function inside, and then essentially just drop it in the create transform func and override this function. And then you can easily use it in your pipeline, basically hiding all of the computation from the researcher. So next two slides, 2 or 3 slides are about all pairs comparison. So our goal in this study is not only to identify the diffusion topics corresponding to a certain type of law, but also perform an all pairs comparison within each topic, and then use that information to put it in the data frame and subsequently to the GraphFrames so that we can actually do graph analytics, page ranks and Dijkstra minimum cost paths. This is actually a computationally intensive challenge. And the previous researchers in the field have not been able to do that. Indeed, the brute force solution is off and squared, and for seemingly small data set, having just a 10 to the power 7 documents, the number of comparisons we are looking at is 10 to the power 13. There was a nice talk yesterday about optimizing the joins calculations by Vida. Although here, I have to say that whenever we can avoid a Cartesian type join, we have to do that. So the approaches that are the modern approaches to similarity joins out there are variations of the nearest neighbor search, locality sensitive hashing, as well as like a sampling techniques of subset of rows of the TF-IDF matrix depending on the sparsity. That algorithm is actually available in Spark as well. It's called dim sum, but it's not quite applicable in our case. Our approach uses the hashing and clustering techniques. And the first approach is based on the Kmeans clustering. Kmeans clustering is used to identify candidate documents which are likely to belong to the same diffusion topic. Here, the tricky part, I suppose, from the researcher perspective, is to tune the number of classes to split into, which we do using the elbow method. We get 150 clusters for the 3-state subsample, and the total sample uses about 400 classes. And the main it results in 2-3 orders of magnitude or less pairs for comparisons. And inside of each cluster, I do a deterministic similarity join. Although I don't rely on like a Spark SQL or just a broad hash join, I convert it to the RDD and do a two-sided join using the keys, which are also more efficient in this case. And the second approach is using the locality-sensitive hashing. Locality-sensitive hashing is a little bit different. So here we are starting from the characteristic matrix. Then we identify a family of hash functions, and we apply this to every row of characteristic matrix, and to extract the min hash signature matrix. Each value here in the min hash signature matrix is the row, or in this matrix, the first row that has 1 in it. Usually in LSH, we split the signature matrix into the bands, and we apply hashing like a band by band into a set of buckets. And then we determine whether 2 documents are likely to be similar depending on how many bands are hashed into the same bucket. In fact, there is a version of the min hash LSH available currently in SparkML starting 2.1. So we've tried going, now that we have identified the collections of documents using these 2 alternative workflows for which we calculate all-pair similarity, we need to let me talk more about the similarity measures that we use. So we actually tried various measures available out there, including Jacquard. So the Jacquard, here we have, I have to say that there's 2 different varieties. One uses the key distance, considering the feature vectors as sets of indices, and doesn't care about a frequency of the n-gram and the token, and also the hash distance. So what I use is the key distance here, and cosine, as well also Manhattan and Hamming distances. So based on the test, the best performance for the workflow one is with unigram TF-IDF, truncated SVD, and cosine distance. However, the min hash works best with a larger n-gram granularity and the Jacquard similarity. Next, onto the interactive analysis. So once we've performed the most data and compute-intensive part, we continue with the interactive analysis. We need to be able to do aggregations, histogramming, and plotting. For that purpose, we introduced the histogrammer tool. This is the language-independent specification, which provides a set of aggregation primitives. The current most advanced implementations are in Scala and Python, but there is also other language bindings for Julia, for instance, and Haskell. So unlike RDD histogram, there is a RDD histogram method available in the core Spark. It also allows to build and fill two-dimensional profile histograms, sum of squares, statistics in an easy way. So here at the bottom left is an example code snippet, what you can do with a histogrammer library on a data frame. So here you can basically define a user-defined function, and you can pass it over to the, you can filter your data frame, and then you pass it over to the, like a bin method. And there is other primitives as well, specifying the column name and the number of bins and the range. So it's very nice. One of the pluses, if someone tried to do like interactive analysis in Spark REPL, the problem is like there is no easy plotting front end. So I'm assuming most of what data scientists and researchers do, you have to output in some format like JSON or Parquet, and then read it back in Python and plot it in Matplotlib. So histogrammer solves this problem as well. It provides like wrappers to the Bokeh and Matplotlib, and allows you to plot, produce nice plot. One other comment that for the aggregation, it's a distributed aggregation, so it can work with large data sets, and it uses this Spark's aggregate primitives. However, it differs from it in some way, and I can talk more about it if you have questions. So the second thing that we do after the similarity join, once we obtain the data frame which contains essentially node the bill, document bill identifiers and the similarity, the column which shows the similarity between the bills, we can easily put it on the graph, considering the nodes with the bill ID, as you can see here, and we assign the similarity as a weight to the edge nodes. One of the advantages of the GraphFrames to libraries like GraphX, for instance, is that it has nice data frame-based API, so it integrates well with SparkML. Speaking a little bit more about the application of the policy diffusion detection tool, so I don't show much results, like scientific results in that presentation, trying to go over technicalities for the most part, but there is going to be a publication soon. And the typical questions that this code allows us to answer is identifying groups of diffused bills on a given topic, like the stand your ground bills that I mentioned in the beginning, also cyber stacking or marijuana laws, for instance. It can use in the mode when we just want to do discovery of topics. Maybe we want to search for a topic that we haven't considered in the beginning. And also for specific topics, we can identify minimum cost path between the bills on the graph. And also a possible application is to determine most influential states for policy diffusion, but this is kind of, one can argue that this is an obvious question, like the most influential states are typically California and New York as it comes to the legislation. So a few more words about the performance summary and the details about the Spark configuration. So the applications have been deployed on the SGI Linux cluster with high memory nodes. I use 40 executor containers. each using the 3 executor cores, taking advantage of the ability to do multi-threaded processing within each executor. I haven't taken advantage of the multiple threading on the driver because I would need a lot more resources, but technically that's the one obvious way to scale out. And I use 15 gig RAM per JVM. Allocating more memory usually leads to garbage collection overhead. So some tweaks were applied to the shuffle, and I use external shuffle service in Yarn. And so since this involves multiple joins, this is obviously a shuffle-intensive task. And there's also some tweaks one can do by creating the custom partitioner for your application and make it available for the join. So I increased one of the key configuration parameters for the Spark that I would identify is the Spark shuffle memory fraction, which has been increased to 0.6, and it actually was kind of changing positive impact on the performance at the order of 100 CPU cores here, as you can see on the plot. And as it comes to the parallel efficiency, which is calculated as the ratio of the single executor performance divided by the n executors times the number of executors, I observe better performance with the larger data sets, which approaches 80% at around 100 executors as well. And that's all for my talk. So let me just say what we did. So we've evaluated Apache Spark for the data-intensive machine learning problem of policy diffusion detection at scale. We provided scalable solution for all pairs similarity calculation based on Kmeans and mean hash. And we also implemented ways to do the interactive. We put it all in the pipeline and implemented the ways for a user to do interactive analysis with the histogrammer package, and also took advantage of the GraphFrames. So tuned the Spark internals, including partition and shuffle, to obtain good scaling up to order of 100 processing cores. And yeah, that's all. So the histogrammer is available on Maven Central. The Scala version is available in Maven Central. And if you would like to contribute, please let me know. And also, the Python version is available in pip, in PyPy. So the rest of the code is available in my GitHub, and I can share the link if you would like as well. Thanks a lot. That's all.
Okay, thank you, Alexey. Any questions for him, please? Oh, a few hands go up. Okay, we'll start from the front here. Thank you.
Hi, Alexey, great talk. It looks like this has a lot of use cases in the business as well. I have two questions. One is on the data science part. How accurate was your similarity that you generated out of this particular application? Were you able to benchmark with some other algorithms? The second question is, I've seen that you've tried to optimize the Spark. Were there additional bottlenecks because it is a very memory-intensive operation?
Yes. So as it comes to evaluating the accuracy of the classification, we do that since this is an unsupervised learning problem, right? So we have a set of documents which don't have labels. So we identify manually labeled subset, and we score it on that subset using the precision and recall usual metrics. And we've got, on the stand your ground builds, we've got some good accuracies. As for, and more details will be in the paper. So that wasn't the goal for today. As for the performance tuning for Spark, what question in particular do you have?
The bottlenecks that you found, and
Yeah, indeed. So there is a few bottlenecks. So indeed, for some workflows like machine learning, one can argue that using GPU architecture and taking advantage of GPU is the best way. So here we do multiple joins. So this is a computation involving large shuffle. So and it's also a data-intensive task. So for this, Spark looked like a good architecture framework to use. Typically, the most difficult parts to tune is the partitioning and the shuffle. So take a look at the custom partitioning. So by default, we have hash partition in Spark, and take a look at range partitioner, and there's a way also to define your own. And also tuning the Spark memory fraction used for shuffle allowed to avoid errors like lost executors. I suppose we can talk more offline. There was a lot of things.
Thank you.
Any more questions?
Beside the min hash and like Kmeans, which are known to be approximate solution, did you consider some of the exact solutions like prefix filtering, L2AP, or others?
What exact solution? Sorry, can you repeat
Prefix
the
filtering or all-pair algorithm or L2AP. There's a couple of family actually of algorithms that consider like inverted indices kind of solution.
Yeah, as you correctly said, this is the probabilistic solution. So the brute force approach simply didn't work. And actually, the first workflow, it relies on K-means. So we have some uncertainty, like on what documents get clustered. So we don't always, if we don't tune it, for instance, we don't always get the right documents clustered in the way we need. But inside the document, we do deterministic similarity join. And when you do min hash, there is always a trade-off between the accuracy and performance. So by increasing the number of hash buckets, you can get like better performance, but it comes at the cost. I will have to ask you the details about the methods, other methods that you used, which we have not tried, and I would be interested to try it.
Alexey, another question here. So.
Yeah, I'm curious what your deployment environment looks like. Are these jobs that you're just running on sort of a one-off basis, or do you have this available all the time? What does that look like?
Yeah, we have on-prem hardware at Princeton University, so it's available for us 24/7. So it's not a cloud-based like AWS. Yeah, and it's a standard Cloudera distribution of Hadoop, deploying applications with Yarn. So in that sense, yeah, it's available 24/7. I can share the details. We actually have all of the configuration in Puppet. We manage this using the Puppet system orchestration tool.
And are you rebuilding models on a regular basis, or like I'm just kind of wondering how often you use these results?
Oh, rebuilding the models. There is a way to checkpoint the models. For instance, the models in this case would be the Kmeans and LSH. So there is, yeah, definitely a way to checkpoint the model in Parquet and start off at that points. And also for the feature extraction, we usually use like intermediate Parquet storage so that we don't have to rerun it all the steps multiple times. So in that sense, yeah, we can do the model checkpointing.
Thank you. Any further questions for Alexey? Okay, one more.
Thanks. I appreciated the description of the pipelines early on, the pre-processing. Can you go into a little more detail of once you get to GraphFrames, when you're like, what graph algorithms are you using, and how is that helping answer the policy diffusion question?
Yeah, so I use currently we use what's available in GraphFrames, and it's actually some of it is reused from Pregel. It's like comes as a wrapped code from Pregel. So use PageRank, and I use Dijkstra, the mean cost path. Actually, if you want to see more, there is basically I have a package on GitHub which shows what I do.
Okay, great. I think, thank you very much. Then please show your appreciation. Thank you.